What if I told you that the difference between an app that feels lightning fast and one that's just painfully slow usually has nothing to do with the hardware? Nope, it's something much, much more fundamental. Today, we're going to pull back the curtain on the secret engine that powers high-performance software.
We've all been there, haven't we? Just staring at a loading spinner, tapping our fingers, waiting. Well, the answer to this question is the absolute key to building software that can actually handle success. It's all about something called data structures and algorithms, or DSA for short.
All right, let's get right into it. We're about to uncover the core principle that really separates those snappy, responsive apps from the ones that just make you want to throw your phone.
Look, you can always throw more powerful computers at a problem, but that's just a band-aid. It doesn't fix the underlying issue. The real, lasting solution, it comes from the elegance of how you organize your data. It's all about being smart before you even start asking the computer to do any work. So, to be smart with our data, we need a way to talk about it, right? A shared language to measure performance. This next part is all about the essential vocabulary that lets developers actually measure, compare, and ultimately optimize their code. The easiest way to think about a data structure is as a specialized container. I mean, you wouldn't store soup in a filing cabinet or your important papers in a big soup pot, right? It's the same in programming. Choosing the right container for the job, whether it's an array, a hash map, or a tree, is always the first step to writing efficient code. So if the data structure is the container, then the algorithm is the recipe. It's the step-by-step instructions for what to do with the data inside that container. A good recipe gets you the right result, sure, but a great recipe gets you that same result way, way faster. And this is how we judge those recipes. Big O notation. It sounds kind of scary, but it's not about measuring time in seconds or minutes. All it is a way to describe how much longer your recipe will take to run as you add more and more data. It's the universal language for talking about performance. And this right here, this is why it matters so much. Just look at the insane difference on this chart. For a million items, a naive, kind of clunky solution, what we call ON squared, would take 1 trillion operations. Yeah, 1 trillion. A decent linear solution, ON, takes 1 million. But an elegant logarithmic solution, O log n, it takes just 20. 20! That's not just an improvement, that's a whole different universe of performance. And here's the kicker. Let's say your app goes viral and your data doubles from 1 million to 2 million items. That linear algorithm now has to do 1 million extra operations. It's working twice as hard. But the logarithmic one, it barely even notices. It just takes one single extra step. This is the magic. This is how you build systems that can actually scale. Okay, theory is cool, but let's make this real. We're going to look at 3 classic problems that perfectly show how picking the right data structure and algorithm combo leads to a solution that's not just effective, but incredibly elegant. So here's a famous one, often called two-sum. Imagine you've got a list of numbers and a target number. Your job is to find any 2 numbers in that list that add up exactly to that target. How would you do it? Your first instinct might be to just check every single combination. And that brute force method, checking every pair, is that O of n squared we talked about. It works, but it gets slow, fast. The DSA approach, though, uses a clever tool called a hash map. And with it, you can solve the problem in a single pass. That's O of n time, blazingly fast. Here's a simple way to picture it. Imagine you have a notepad. Your target is, say, 9. You look at the first number in the list, maybe it's a 2. On your notepad, you don't write down 2. You write down the number you need to find, 7. You go to the next number. The moment you see a number that's already on your notepad, boom, you're done. That notepad is your hash map. It's like leaving a breadcrumb for your future self. Okay, problem number 2. You've got a huge, perfectly sorted list, like an old-school phone book. You need to find one specific name. You're not going to start at A and read every single page, are you? Of course not. Going page by page is a linear scan. That's O of n. But since we know the data is already sorted, we can use a much, much smarter algorithm, binary search. And this takes us all the way down to O of log n, which, as we saw, is incredibly efficient. It's pure divide and conquer. You go to the middle of the bookshelf. Is the book you want before or after this point? Whichever it is, you can completely ignore the other half. You just threw away half the problem in one step. Then you just do it again and again. You zero in on the answer with incredible speed.
All right, our last problem is one that code editors and compilers are solving constantly, thousands of times a day. They need to check if all your parentheses, all your brackets, all your braces are opened and closed in the correct order.
Let's use an analogy. Imagine you're walking down a hallway with a bunch of doors. Every time you open a door, that's an opening bracket, you grab its key and put it on top of a stack you're carrying. When you get to a closing door, you have to use the very last key you picked up, the one on top of the stack. If it's the wrong key, or if you don't have any keys left, you know the path is invalid. That last in, first out logic, that's exactly what a stack data structure is built for.
Okay, so there's this really common idea out there that this stuff is just homework, that it's only for passing those tricky whiteboard interviews. Let's just go ahead and put that myth to rest right here, right now.
You hear it all the time, people complain about it, but the honest truth is, these concepts are the literal bedrock of almost all the software you use every single day. This isn't just trivia. These are fundamental engineering tools. Think about it. That undo button in your editor, that's a stack. The caching system that makes your favorite website load instantly, that's using a hash map. The database indexes that find your data in a millisecond, they're built on trees. DSA isn't for interviews. DSA is for production, period.
So the big question is, how do you go from just knowing about this stuff to actually mastering it? Well, it's all about active practice, not just passively watching or reading. Here's a super simple but really powerful way to get started.
It's a 3-step process. 1. Pick a single problem, like that two-sum problem we talked about. 2. Code the solution yourself, from a blank screen, no copy-pasting. And 3, this is the most important part, explain it, out loud. Explain the logic, why it works, and its big O complexity. To a friend, to your dog, to a rubber duck on your desk. It doesn't matter. Articulating it is what cements the knowledge in your brain.
And that's really what it's all about. The goal isn't just to memorize algorithms, it's to start seeing the world and the code you write through this new lens of efficiency. So I'll leave you with this question. Take a look at your own projects, your own code. Now that you know these patterns, what slow, clunky process can you make better? What can you fix?